started. The idea is by the end of this week, I would like you to be able to have a script and turn that into a containerized package that then you can reuse. And then you'll see it by examples, and maybe I practice we can do together on how to get there. But at the end of the day, don't see that as a very, software engineering is complex. And in the sense that I work with a software engineer now, like I know nothing about VS Code debugging mode, but I think by the point is you can use templates, you can learn the principles of them, you can learn how to test, and I think you can get to a nicely containerized package over time. So there's a very nice talk that was given by Lueda in the Spin workshop. So the talk is actually a nice YouTube video online. And I really enjoyed the way he presented how to get to open source software. And I love the spectrum of what an open source software package can be. And you should all consider this as a spectrum, and that any step is a positive step. You can see the minimal one is being, sorry, I'm just gonna kill Slack, is that you can put in journal supplements, just like what Dave was showing at the beginning in his 2012 paper. You can attach a zip file of your code, or you can have it on Zenodo, just as is of all the software that you've used for your paper. That's the first level. The second level, it said, okay, I actually use GitHub, so beyond just Zenodo, and I have one commit and I have a README that describes the code. And that is linked to the paper. So that's the next level of it's using this version control aspect of code repositories. And then you can go with the next step and say, my GitHub also contains documentation. It provides a guide for contributing. It provides testing. And beyond that, you can say, and my package is a Python repository, that a package that's downloadable, installable with PyPy or Conda. And I also include automated testing and deployment and all that. But all these steps, basically, you can, if you take the first step, this is the good one. You get started with there, and you slowly learn how to build up on these skills. These skills at the end are actually quite complex, and software engineering degrees are almost necessary to do this well. So just see that as this progression on how you can make your software more open source, and then learn as you go, and any bits is success. Very important thing to note is a code without a license cannot be reused, modified, or extended. And so actually I had this issue with one code that we wrote, and the testing part is another repository that's not licensable. So actually we cannot reuse it for the next step, for next iteration. And so it can become a technical problem. Using GitHub, it's very easy to just have automated linked licensing. Licensing is an entire field of its own. I just by default go with MIT license, because in the data world, we tend to have a lot of homegrown codes. And so it's easier to just go with the simplest one. But this can become more complex as you start using dependencies that have other inherited software integrated in them or so on. So I won't provide a lecture on that, but there is we can talk about offline what that some resources on how to get there. Why we want to do open source software? You saw some motivation earlier. Others can reuse your code and benefits from your knowledge. Savoir-faire, some French accent there, and you don't have to reinvent the wheel. And so that is saving time for everybody. It forces you to be organized, clean, and structured. It's not just because I'm a mom, but if you're not organized and clean, it really delays progress in science. So you gain efficiency and productivity by being well organized in your code. It really helps debugging, because then people know how to post GitHub issues. It really helped meet new people. I actually found collaborators on GitHub because I like their projects. You can find new mentors, because some of these developers distributed in the world can teach you good things. And you can actually build a reputation for good software practices. It is your new CV. It is actually how I motivate supporting the development of the code, is how many forks do I have on my GitHub? How many likes do I get? And so actually being online with GitHub and being polite when you submit issues, being considerate, this demonstrates your skills as a software engineer. And let's face it, if you want to become one, you'll make a lot more money than a faculty. So it's a good skill to learn. How can we do this? You can use hosting services. So you'll see this linked on the slide, but GitLab is more open source. GitHub is owned by Microsoft. I pay for it. I don't care. It works. It's well integrated. Bitbucket, I think, was a very popular one, and I'm sure you know of others that I'm not listing here. I personally use Denolle to then get the DOI for my code that's on GitHub, because there is this nice integration, but there's other ways that you can get a DOI for your software. Try to follow best practices for software, and we can talk about for Python. There's a type of syntaxing that you can self-impose or have actually your editor management like VS Code impose it on yourself to be a nice style for coding. And another way to actually participate in open source software is to contribute. You don't have to create something from scratch and then have to start from zero and have to demonstrate everything. Actually, I would like to motivate you in this lecture that we should actually be more collective in the way we develop codes. And so one way to participate and learn is to contribute to an open source project. So I will be calling out for new developers for my noise seismology code. It teaches you how to build good coding habits, maintaining good coding habits. It demonstrates your technical abilities. That's your CV for data science future jobs, maybe. And it really helps provide a favorable reputation. It's not the social media or the online presence. It is literally about your software practices and leaderships. So I'm gonna drink some coffee, but I inspire some of these notes from a really cool program in data science run by CU Boulder. And so some of these slides are good standards that I think some grad students, even in my group, are not always practicing. And I think we should talk about this. Something that Dave brought up with the formatting issue in his supplementary materials. It is very important to use standard operating system agnostic file formats. CSV, Markdown, text, whatnot. These are standard. Avoid PDFs. Only ChatGPT can really ingest PDF at this point. Even Word doc or Excel-like documents are readable by proprietary software. And so what you should strive for is finding ways to just have data and metadata in open source formats. And yeah, naming files, super important. It can get so messy. Name your files consistently. Keep them short but descriptive. Avoid special characters, spaces, no spaces. If you use Linux, it's going to be a problem. Keep them machine compatible. You can use underscore to help make the file name look human readable. Avoid capital letters or case sensitive characters because some languages won't recognize uppercase or lowercase. Be consistent with date formatting. I'm guilty of that. You'll see tomorrow in NoiseSpy, we don't have a consistent, we have another type of data format, but you could say I will use this data format for dates, formatting for dates. You may want to include a version number when you have your code. It's always good to go back to the version that did not have the bug. So be mindful that once you have a version number of a code or a figure or everything, you'll be able to go back to it. You can share the naming conventions when you work with collaborators. That is maybe included in a README or whatnot, but you can explain why you choose to use that naming. And then you may want to record your naming convention in some kind of data management plan or software management plan that you would attach to your projects or your GitHub. Some examples here. You can see on the left what's not great. You can see on the right what's something you actually can read. My abstract.docs. What did you? 2022? 21? What conference was that? What topic was that? This is too indescriptive. We don't know. You're going to lose what this is about. This file name that uses Excel is very long and it uses spaces. And so if you actually want to use Shell to automate file management, you're not going to be able to read for the majority these files. Figure 1 space.png, fig 2, all of these with spaces will be problematic. You may want to think about formatting them not super long, don't append all the parameters that you use for making that figure, but you could use them as, you know, this is a histogram about the attendance of the talk. And so you can actually have a short description. And here you can just attach all of these by just using this dash and be good with it. Okay, computational workflows, we could have an entire week on that. So I'll just give you one slide. It's a good practice to modularize the code. I'm saying that by experience because you will see NoisePy tomorrow used to be this one block, 1,000 lines of a module with all the functions in them. And as we're refactoring it, it's taking a lot of time for the software engineer to see what function was doing what, when is it called, and making it very difficult to modernize and contribute. So learning by experience, please don't do like me, create very simple functions. This is an example in Python, quite descriptive with the parameters input and output describe everything. And then, you know, it does one task. Anything that's repetitive should be a function. Have a couple of inputs, a couple of outputs, nothing too crazy. You can cast them in objects if for inputs. One function, one task. So then if you want to test it, you can just have one test for this function and it does exactly what it should be doing. Keep it small, focused. You can combine functions in additional wrapper functions, which may create some kind of complicated kind of a network, a web of usage. But if you describe well what the code is about, the software is about, I think it's readable. It makes it easier to update the code. It makes it easier to test the code. And if you're using Python, there are some guidelines about what good style Python is. It's called PEP8. And if you click to that link, you will see recommendations for indentation, variable naming, defining functions, and things like that. You can have it self-imposed and follow this guideline. And I'm learning actually new ways that you can have it integrated in your code editorial software like VS Code, and it will automatically format it the way you want. So I'm lazy and I like this aspect of gaining efficiency. Expand your code with checks and tests. It's something that I think is good scientists promote that in their research group, and I feel like I've lacked at that, but we need to be more mindful of testing each functions because as I said, we can reproduce bugs. And so ideally we want to not have bugs in our code and at least have the correct workflow. Again, from Earth Data Science, a little bit of a flash on what is a good well-organized project, what is non-well-organized project. Same thing for your GitHub, same thing for your Dropbox folder for your plots and papers. Describe the folder, put the scripts in one folder, maybe the data in a different folder, what's an imagery, what's not. The outputs of your analysis could be in different folder, the final paper can be that. What's not well organized is file naming that's not consistent, a flat hierarchy of where the files are. And so try to avoid that to be able to go back to it, maybe 10 years later, and try to reproduce it. There are tools to visualize workflows. And this is an example. What you can do this is an example from Assets. That was a NSF funding project, I think, to actually document and publish workflows, not just the code, not just the narrative in the paper, but also the workflows. So here, what's interesting about these visualizations is we start from the top where the data is ingested and we see all of the processes, the types of data, where they get fed into. And I think some papers in seismology have that just to describe the actual workflow. And I find them extremely useful to get this overall view of what the software is doing, especially when it's a complex software. So find a way to even put that in your paper as a way to describe where the data is going, that type of operations and things like that. We actually find this is the way some of the distributed acoustic sensing interrogators ask you to design your process is by actually having these workflow charts. So it's actually becoming it's quite useful. So now I wanted to briefly talk about the ecosystem in seismology. for software. And we represent maybe like 2 or 3 types of seismology in this workshop. And for the heavy computing piece, we have the ones that solve for the wave equation numerically. So it's a theoretical numerical exercise to predict stress and strains and waveforms in a complex medium. So predict the wiggles. Sorry for that simplification. And I'll talk next about what is the data analysis aspect. And so I don't want to oversimplify this, and maybe Alice, if she's around, can talk about this, but the common points of a lot of the modeling software in seismology is that it is solving the wave equation. It is solving with different numerical methods, with vast range of scales. And the most efficient way to do this has been to develop them in C++, in Fortran. And this is a theoretical problem that has been recognized for decades now. And so there's been long, well-organized teams that develop these codes. So the leading codes for wave propagation are SpecFem, and it was supported by CIG. It is supported by Scoped. It was probably supported by other sources of funding. It has over 200 publications that use that same software. It has over 30 contributors, and it's been really developed for 20 years. 20 years of development for one code that has enabled so much in understanding wave physics, wave propagation, earthquake hazard, and whatnot for one software. The one that Alice has been steering is Seisol, and I think it does wave propagation and earthquake dynamics, and you'll have a hands-on exercise there. And it's got, it's received a lot more recent funding in the past 5, maybe 6 years or more by European sources of funding. So you can see the links here on Cheese and NSF LCCF for the US part of it. And if you look on their GitHub, they have over 65 contributors to that software. And so what is very neat about this is you can see the coalition, the gathering of the community on like a couple of pieces. SW4 is another CIG supported software. It has maybe 13, but I'm sure over 13 contributors. Excuse me. It's also quite used in the, at least in the Western US, I've heard a lot of people using this code for nice adaptive meshes for ground motion simulation for hazard. And so I don't want to summarize it because it's not really my field, but I see dominant, huge teams around one code for wave field simulations. The big data software, to contrast with what I just showed you, is very eclectic. And I represent NoSPI. It's something that we don't have 30 contributors, we have 3 or 4. That was led by former postdoc Chen-Qing Jiang, who's done tremendous work with it. And it was funded for 1 year, and now we're revamping that funding. But you can see it's a much smaller team, and it's much smaller investment of support. SizeBench is the machine learning kind of interoperable platform in Python. It has 13, but a growing set of contributors. And I really like the way it's gathering the ML community together to standardize formats and be the glue of all of these models. Other machine learning models, maybe like FaceNet for face speaking, has over 6 contributors. MSPass that Ian Wang is developing and contributing has seven contributors. But you can see it's very different landscape. We code in Python, in Julia, maybe C++. And the things that we tackle are maybe more diverse, like we do cross correlation, we pick, we have some ML workflows, we extract features, we have data management. And maybe because it's just a more diverse, we are not coalescing over a few codes, and also it makes it quite difficult to develop these codes, basically, if we don't have a team. So I'm hoping that today, this workshop, you'll see a bunch of codes that you will be inspired to help and contribute. Even though this may not be your favorite way of solving a problem, you can bring your cool ideas to make it better. So what could be I'm advocating for an ecosystem for big data seismology. You may be familiar with the fact that the US Seismic Archive, IRIS-DMC, that has provided data accessible to the world for many decades, is moving to a cloud object storage platform in this coming year. As users, you may not see any difference because you will still see the Python API from UpSpy to download. Though I think what you will be able to notice is a dramatic speed in download time, not because of internet being faster, but the backend of Amazon Web Services for storage is so good. You can query 5,000 times the same object. And so it's going to be a lot faster, even if you're not running on the cloud. And so I try to like cartoon, make a schema of what the ecosystem is in big data seismology. There's these glue APIs, the ones that everybody use, like UpSpy, MSPass, and for DAS is DASDay. And these are like community Python ecosystems that allow us to manipulate data, query data, do minimal processing, and pass metadata within pipelines. And I find that these are the ones that are really guaranteeing the interoperability of everything else. And they interact, I guess they will interact with cloud. Anyway, we're working on this, but anyway, the point is these are the pieces of software that most people use to do observational seismology. And then maybe we create some basic data products that are not the science goals, but they enable science. And for that, I want to say machine learning, I think SciBench is the leader in terms of community development. Earthquake detection is also a very common problem. And so we have EQ core scan that's very well developed and by Callum Chamberlain and then RedPy from Alicia Hodovec are these packages that just build earthquake catalog almost from scratch. Then from ambient seismology, we have MS Noise maintained by Thomas Lecoq, and we have a couple that are coming up. So NoisePad that we'll talk about tomorrow, and Seismic from Peter Marcus in Potsdam. And so these are more like big data, aim to be more big data processing. But these really just create data products that then we can use for science. And they sit in this area, querying data with UpSpy or whatnot from these archives. And then what do we do as researchers? We have a full stack workflow, which means we download data from that archive. Maybe we use this data management community software to do that. Maybe we use these other data product community software to cross-correlate or detect or whatnot. But then what the researcher does is this other type of software, which I think I call like the research level research software. It's the full stack workflow. It should be reproducible, provided that we have data that's untouched from this archive and we have open source software along the way. It should have its own repository because it's the full research and investigation. And this is the kind of full stack workflow that can be published in open access journals. And so we in the community focus on this, while we should also contribute to these other projects that really enable our research. But this is more like single PI, single researcher investigation. But this deserves attention as well for reproducibility and be mindful of how do we reuse, how do we cite these other softwares that we use to create our data products and then enable our science. So I'm kind of hoping to gather the community at some point. Vanessa funds me on creating this ecosystem a little bit of gathering people together with this community software, understanding what is the full stack research software and how can we make this reproducible at the researcher level. Also want to do it on the cloud. Wish me luck. A little bit more about definition on open source software ecosystem, which I learned a lot this year. So I'm definitely not the expert, but there's a rich literature on this. What defines the values of a community for OESS is really gathered around a few key points: stability, quality, community, compatibility, replicability, and innovation. And these are the values that the community decide which one matters the most for a given open source software project. And it may depend on the community, it depends on the goal. So I just wanted to give an example, and we can debate on that, of course, is given this kind of landscape that I drew, I think that we need stability and quality and community inputs to these archives. We need the compatibility to be the strength of this data management community software. We want innovation and replicability for all of these other like cross-correlation of machine learning workflows. But then what we should really push is innovation at the researcher level, because this is what will drive progress in the rest of the scientific community, and also of the need for development for these other ones. But often this means that these software don't get updated that often. They have to be stable. We don't want a version to be updated every, no more than once a year. These also have less frequent updates to be stable and compatible with the rest. They have to be aware of the rest. These can be updated more frequently, and this is of course like the one shot. You use your GitHub to commit every time you have an update to make sure you save your workflow. But there's different level of frequent updates and kind of values on what you should value for, or principles for these software. What is coming now as recently is following the FAIR for data. Now we have the FAIR for research software. So there's a body of literature on that as well. So research software is defined as including source code, algorithms, script, computational workflow, executable during the research process. So in a way, I see more like the research level full stack as being a research software. Here are some of the guidelines. We got DOIs. We got describe with rich metadata. We get the metadata is retrievable and standardized protocols. Software is both usable, so you can execute it, and reusable. You need to be able to modify it. It's not just put a container and good luck. You have to be able to understand what's under the hood as well. Okay, so that's it actually for me in terms of kind of best software practices. We didn't get into more of the nuts and bolts on how to design good software, but I hope that with Ian's lecture and our cloud workflow, and maybe later on, asynchronous will provide more guidance on prioritization and things like that. All right. Great.
I guess I should be leaving.
Yeah.